Muito bem, boa tarde. Bem-vindos à segunda aula do curso do professor Ascher. Vamos lá.
Obrigado.
Por favor.
For people who have not been here on Tuesday, let me say que eu posso falar português lentamente. Se você tem perguntas, você pode perguntar em português. É possível que eu vou entender. But I will speak English. So this is the second in a series of 4 lectures that are loosely connected to each other. So each of the topics is distinctly different, but there are some connection through some application, through some issue. And today's topic is the manipulation of data, especially completion of data, but also other manipulation of data. Data science, I think also here, but definitely in North America, is a huge thing. And there are centers of data science in almost any university. Every day there are new ones. My own department has a master's thesis in data science, which is professional, which means we get students from outside and pay a lot of money to take the course, and so on. But often in data science, or maybe data science, I'm not sure, the assumption is you have a lot of data. And the question, what does a lot of data mean? There's a question there. It depends on the situation, whether the data you have is a lot of data or there are some holes in the data. And when the data don't sit very well with your theory, sometimes people make assumptions to simplify matters and continue. And that is what I mean by manipulation. Okay. So we will see a bunch of examples on that. But before we get to examples, I will try to motivate this further, and then discuss the following topics. You have scarce or sparse data. I will explain what that means, and people try to complete it. It comes also in different ways. You may have uncertainty in location of data. You make measurements, but there is uncertainty at the location of the measurement. Not just the value of the data, but the location. Sometimes, that's actually the most exciting in some sense. Some people say, if I don't manipulate the data, I cannot solve the problem. Forced to cut corners, I wrote. Yeah. Cut corner means curtir a esquina. Is it possible to say that? Oops. No. And then at the end, I'll talk about the randomized algorithms for many data sets. And that will bring us to the next lecture. I have not invented manipulation of data. There is a company that sells T-shirts online, of course. You can get a T-shirt like this. Yeah. So people realize that when you massage the data, you are committing a little bit of felony, a little bit of sin. Yeah. But like drinking, that doesn't stop us. Yeah. And people do it anyway, even though they realize that there are some errors generated. For example, we generate errors, and then we fit the model to fit our errors in some sense. Yeah? You have to be careful with that, and this is really what it is about, in a sense. Here is a list of ways in which people often cut the corners. Yeah. So again, I will concentrate with 2 examples on you have a physical domain, let's say. Maybe it's not physical, but it's a domain in 2 or 3 dimensions, and you have data only at some points of the domain and not everywhere. What do you do? I will talk about this in detail. Or you want the data to be on a regular rectangular mesh because it's easier to work with on the discrete level, but the data are not exactly on a rectangular mesh, so you move it so that it will be on the rectangular mesh. And geophysicists do it all the time. Or completing the data to obtain more efficient algorithm. This is what I will talk about in the last example I showed. This is the scene of the mathematicians. Yeah? We have some sort of EIT problem, and we assume we have data all over the domain. That means that we've somehow measured infinitely many data. Actually, it's not just infinitely many. It is not even countable. Of course, it is an approximation. Yeah? And again, the thing that in some sense is the most alluring, people say, it's not just that I'm doing it for convenience, it is that I must do it or otherwise I cannot solve the problem. Yeah. And so the question is, when is it okay, not if, but when is it okay to do this? When do we get away with it? Yeah. And when not? And so we're going to see case studies, all of them case studies I know, but this is not meant to emphasize what I've done, really not. I'm too old for that. But it is rather meant to tell you what we've done, because I know what we have done much better than I know what other people did, yeah, in a natural way. I know what is under the hood, they say in English. So, so this is from geophysics, from exploration geophysics. You want to find gold or oil or something like that. This one is a common work. We have two co-workers here together, myself as well, but Joe Zubelli and Xu Yang sitting over there. And in fact, it is Xu's work more than anybody else's. And they will be happy to answer your questions on this one. Denoising, I will talk about this again in my last lecture on a week from today, Thursday, next week. And then this one I talked about last Tuesday, 2 days ago, about this application. There was some data manipulation there too. And this one I will talk more about next Tuesday. Okay, the setting, I will actually even write it down so that it will not disappear once I switch the slide. So we have data D. And we are looking, so data, and we are looking for a surface function somehow, a function of a few dimensions, let's say M. And we are going to discretize it somehow eventually, and so we might as well talk about a vector M of unknowns, like we did last Tuesday when we have this Q, which were nodes of a triangular mesh, or in 3 dimensions, a tetrahedral, okay? The same thing here. This is the M, the unknowns, okay? And for each M, we have a forward operator F, involving some inversion of a differential equation. And f of m for each m will predict what is the data, okay? And so now the question is to find an m such that the observed data D is equal to the predicted data, f of m, plus noise. Everybody with me? This is important to get to get used to my notation. It's important to get used to my notation. Okay. And so now in particular, we are going to look, I think that is even in the title of the thematic year, we are looking at PDEs. And so in fact, we are going to assume that the f of m here involves a differential equation that is linear in the field U, but usually nonlinear in M. Okay. M are coefficients in the PDE. The PDE itself is linear, so U, this field, is given as a Green's function times a source Q. So you have a linear operator operating on U equal Q, and therefore we write it as G of M times Q. And then we have the field, and now the data have locations, and we sample the field at those locations. P is the projection matrix that says what are the locations, and that will be our predicted data, PU. Now, everybody looks at this sort of data misfit objective function. You take the predicted minus the data, the predicted data minus the observed data, and you want to try to minimize to some extent the least squares difference between them. And this is a reasonable thing to do if, in fact, the noise is a normally distributed variable. We assume typically that this is the case. And so if it's normally distributed with zero mean and standard deviation sigma, and so this is the correlation matrix here is identity as well, then not only this is a reasonable thing to do because it's maximum likelihood, but also we have the discrepancy principle that says that we want to iteratively find m eventually such that phi of m is below a tolerance rho that is given by sigma squared, the volatility, constant volatility, times, this is not identity, this is L, the number of data from here. Okay? So LaTeX does funny things with L and I. It's almost the same symbol. Okay, so this is identity matrix. This is L, I don't know, 55 or something. Okay? And this is 55, not identity. So there's nothing to do. You have a principle that says just iterate until that tolerance is hit and we are done. If life were only as simple as this. But sometimes, well, always, in fact, life is more difficult than this. And so let's look first at just completing scarce data. I call this scarce because everybody uses the word sparse. Sparse matrix, sparse solution, now it's going to be sparse data. So let's call this scarce to be different. Okay. And this is the first case study that I mentioned from quite an old, this is actually, the work was done around the year 2000, and this was the kind of summarizing paper of a project. And so the PDEs that are involved here are Maxwell's equations in the regime of parameters where it is like a parabolic with lots of damping, which you solve either the frequency or time domain. And M is conductivity, or 1 over conductivity, which is resistivity. Okay. And this experimental setting is actually a real one. It was given to us by some company, by a mining company. It's from Mexico. I think it's called Pensaquito. No one has ever been there. It's a hill that some mining company got bought the rights to dig there and find out what's inside and become rich, if it makes sense to actually do it. So they wonder whether they should dig there and make a mine and so on. Yeah? So for us, of course, they will not give us the data because that's how they make the money. But they give us the setting of the experiment. So everything here is real except for the boxes that we put there ourselves in order to be able to compute the exact solution. Yeah. So, and then you compare what you do to the exact solution, and then you may or may not be happy. So let's say that what corresponds to the boxes there is M star, an exact solution. And it's a big assumption, in fact, to say that there is an M star. But let's assume that there is an M star, an exact solution. So this is a sandbox, you can think, with boxes inside, except that the sandbox is 10 kilometers here, 4 kilometers here. It's a big sandbox. Okay? And it doesn't have to be, of course, only sand. But this is, I don't know, gold, another metal, iron, whatever, some material. Again, we use this only in order to generate data. Then what we do usually is we pollute the data with noise, and then we try to recover by our methods the result and compare. The data are measured in such a situation. This is, again, we are back to real life and not imaginary boxes. The data are measured on this loop here. That's the survey area. You have a helicopter flying above and measuring electromagnetic field. The thing is, therefore, that the data is not given everywhere in the box. It is given only on this loop. What this means is that to make phi of m as small as is possible, you can do in I don't know, infinitely square ways or something like that, you know? It's just the number of data is much smaller than the number of degrees. Just imagine using some mesh to discretize the box. Yeah? It would be a three-dimensional discretization, and you really have data only on a loop. Yeah? So this discrepancy principle, the Morozov's principle, loses a lot of steam right away. There will be infinitely many ways to satisfy the principle. Okay, so what do you do? So you want to interpolate the data in order to get that data everywhere, and now the Morozov principle becomes more realistic again. But of course, your problem becomes less realistic. And I do not know of any geophysicist who was bold enough to suggest that we should actually take this data and interpolate it on the entire three-dimensional cube. It makes no sense. It's not a cube, it's whatever it is. Okay, so in this case, the amount of data is so small, is so scarce, that you are not going to interpolate it. I hope everybody would agree intuitively that this is too much. If you can interpolate this data, or extrapolate this data to fill the entire box, why do you need the PDE? Who needs Maxwell? You know, it makes no sense. Okay. And so what people have done in geophysics is to, in fact, solve problems with this small amount of data. And of course, you have to now add a prior. And so the Tikhonov regularization is not just any Tikhonov regularization. It is not in order to make the problem more well-posed, not only to make it well-posed, but also it is a prior information. For example, that this M has to be a smooth, where is it? M has to be a smooth function, maybe. Or in fact, in this case, it will not be smooth, but it will be piecewise smooth, you would think. So you introduce some prior that reflects the idea that your M should be piecewise smooth. Okay. Again, not any Tikhonov, actually, not any Tikhonov at all. It has to be something with the reality of the situation, so a particular prior information, a true prior information, in order to be able to come up with solutions that not only do something for the data, but also are close to M star. The other thing is that in this kind of problems, diffusive problems, it is much easier to make phi of M less than or equal than some rho than it is to make M close to M star. What we want really is to minimize the computed M and the exact M in some norm. We want to minimize this. That's what we want. That's what we have. That's the difference, yeah? We don't have this, but we have phi of M. We can evaluate phi of M for any M, and that's why we measure this and we reduce that. But it's not obvious that doing this will give you that, okay? And in fact, here is the actual data we used. So we started with, these are different ways of looking at the data. Don't worry about it. Just get an artist's impression of this. That's the clean data, okay? We solved for the forward problem, and that's the clean solution. We perturbed it by Gaussian noise, okay? And then solved the inverse problem, and that's the result. The result is actually pretty close to the clean data that we don't have. We pretend we don't have the clean data. Okay, so the result of the inversion is in fact close. The U, the field U, is close to the clean field U. Okay, much closer than this M is to M star. The M star is the boxes that we had before, and this M, we're actually lucky to have all three boxes showing up somehow, but definitely they don't look like boxes at all. You see, so this one that we want can be much larger than phi of M, the MISFIT. But the MISFIT is what we have. Everybody works with the MISFIT. The important thing to remember is not to work with it, but rather not to take it too seriously. That was case study number 1. Case study number 2. Any questions on this? Case study number 2 becomes more interesting, i.e. more intricate. And this is where I'm happy that George made it to the hall, because my knowledge of mathematical finance is not going to span 90 minutes, or not even 9 minutes. But we've worked on this, and George and Hugh do know what this is about. Okay. So there is that famous Black and Scholes equation. Maybe many people have heard of it. They got a Nobel Prize for it, in fact, in economics in the early 1970s. And the Black and Scholes equation is with this sigma a constant. Okay, not a function of tau k is here, but a constant. And it's a parabolic PDE. And what it is for is you have a stock with a price S0 at the moment, and you want to calculate an option price for it. European option is called. And you have the independent variables are tau. It's the time to maturity. For us, it's just time. And k is a strike price, whatever that means. And C is the value of the call. Okay, this is the one we want. Okay, this is the one we want. And the inverse problem is to find sigma, the volatility. So if you had the original Black Scholes, come to think of it, Adriano also knows about this much more than I will ever know. If sigma is constant, then you have to solve the inverse problem for sigma. However, said Dupire in in 94, the original Black and Scholes does not explain a certain disaster that happened in the financial world in, I think, the late 80s, if I recall correctly. Many disasters. Many disasters. Okay. Okay, I'll take it back. Many disasters. And in particular, there's a curve that, do I sound like I know what I'm talking about? I hope not. There's a curve that instead of doing this, does this. Oops. And that's the thing you want, and this is called the smile. Okay? We want to see the smile coming out of the model. And so for this, in order to be able to come up to actually obtain this from the model equations, Dupire said, let the volatility be a function of tau and k, not just a constant. It's a PDE. And from here on, it does conform to our problem, for our setting. Okay. The first thing about this PDE is that k that appears here, it's unbounded, the independent variable, and therefore this dependent guy will also be unbounded, so we have to non-dimensionalize it. That's the first thing we do. And so we defined y, which is called log moneyness, to be the log of k over S of 0. And so S of 0 is the price of the stock. And obtain this much nicer looking PDE, where m are unknown sitting here. And so we can write it as L of m times applied to u equal q, just like the other ones. And we discretize it with a constant step size in t tau and another one in y. And have this little h here denotes that we've discretized the PDE. Problem is that the data now is not only, sigma is now a function, and so you have a domain, tau and k. And it turns out the data, in general, people say, well, in finance, data is great because you have lots of data, and you don't have to fly a helicopter. You just look at the internet, and there is the data sitting there. Yeah. The problem is that still in the domain of tau and k, you don't have data everywhere. You only have data in particular spots. So of course, the next thing you'll say, this is just Petrobras. But in fact, also with the Standard & Poor, was a private joke here. In the Standard & Poor, you have a similar situation, okay? The most famous general index in the US. So again, you have data only at particular locations and definitely not even half of all the locations of a reasonable discretization. Once again, scarce data. Scarce data means that there is some matrix there, crucial matrix, the Jacobian matrix of F, that would look like this. This will be the number of data, and it is much smaller than the number of unknowns that you have to solve for. And therefore, you have an obviously large null space. And so here, it is not so preposterous. There it is. It's not so preposterous to suggest that we just extrapolate the data to have data everywhere. And that was proposed and done by several people. There's a paper by CARLO from 2005 where, in fact, he said we were going to introduce for the extrapolation, we will have a prior, a financial prior, I called it, that basically produces the smile effect that we are after. Okay? First of all, we say what we want, and then we fix the data in order that it will correspond to that. That's the cynical interpretation. Okay? Nonetheless, it was done, and in fact, Vinicius, who is the only co-author who is not here, did the same thing with bilinear interpolation as well. He's a professor in Florianopolis, by the way, where same department as Antonio here. So, but you can argue, well, this is not so clear, just like in the geophysical case. It is just less, less clear that it is not clear. Okay, because here too, I mean, you have the data produced by the interpolation or extrapolation, and then not the data, but the solution of the PDE. Why would they agree? They may be fighting with each other, in fact, instead of agreeing. So, and it's not so clear that it's a good thing to do. And this is what we set out to do, to look at it and figure out what is better. Which one is better? Leaving the data alone and introducing information versus smoothing M and so on, or introducing this extra data that we generated ourselves and then solve the problem. See? It's clear that, okay. And we used both ensemble Kalman filter techniques, two of them, in fact, and Tikhonov type regularization. And so what you have is our function phi now depends on MH, and UH depends also on MH, and so it's really only MH here. The same thing as before, except that the P now, the projection matrix, is either the projection to where we had data, in the case that we don't complete the data, or its identity if we have completed the data. And so, and now in any case, we add regularization that looks like this. This is Tikhonov. This is a penalty on how far you are from A0. Happens to be a constant that people agree more or less on what its value is. And this is penalizing smoothness in the tau direction, likewise in the y direction. And these are results, typical results. And you see, so these are the Tikhonov and the ensemble Kalman filter, and I forget what else we had there. There are three curves. What are they? I forget which one. But the point I do remember, the point is that if you do not complete the data, then you have essentially the same curve here, independent of the method. Whereas if you complete the data, you have completely different curves with different methods. These methods should not produce completely different results. I mean, they are small improvements of one another. Whereas here, they in fact produce completely different results because we extrapolated the data, you see. So in this case, it's not a good idea to do it. In this case, manipulating the data in this way is not a good idea. And we did it in several other situations, bilinear interpolation, as I mentioned before, and different weights for the Tikhonov prior. And if you say, well, but these are different weights and so on, how do I know that these are the right weights and so on? I think we are going to have some lectures about this, or maybe we already have had. But the point is that then we also have this ensemble Kalman filter. It doesn't have parameters. Okay, it learns parameters from the process itself. And so you have to come to the conclusion, in fact, that here manipulating the data in this way is not such a hot idea. Two other things that I wanted to mention here. We tried two ensemble Kalman filter algorithms, and the way both of those, these are, by the way, excellent people, top people in the field. And the way the algorithms are presented, there is no regularization there directly, okay? But when we did not have the regularization there, those algorithms did not perform well at all. It's only when we introduced Tikhonov type regularization, they performed comparably. And I think that at the bottom of it, there is the conclusion that if you don't have a huge amount of data, and if you just want the gradient, write it down. Don't approximate it by data. Go ahead, any question? The other thing is, once they were fixed, they were not better than the Tikhonov. They're supposed to be better somehow, but they were not better. And I believe that this is because the data is scarce. I think that these methods would be better because they involve more sophisticated statistics. When you have lots of data, when you have enough data for this to make the difference. But if it's scarce, this is just not the bottleneck. So these are actually important lessons to remember in these days when everybody talks about data science. Any question on this? So this is ensemble, not just Kalman filter. It's an ensemble Kalman filter. And these are two methods where they are specialized in a way that the way we treat time is as if it was just yet another variable, not like going forward. And that's what they do as well. They actually particular algorithms for that, for that situation. No one is asking us questions about the model. Okay. Uncertainty in data. This is something that I think most people are not even aware that such a thing can happen. What do you mean? I have data? I have data. I mean, what do you mean that we don't know where is the location? But it happens all the time. For example, so in fact, two examples. One of them I will mention briefly because it will come back a week from now. And another one, the same paper that we just discussed, except that it was 2017 and now it's only 2015. There's a reduction there. And so let's look for a moment at image processing. And that's a picture that I believe most people have seen here before. I imagine somehow very popular. It is a name, a picture with a name. It's called the cameraman. Terrible picture, by the way. And it is like that, but it is given to you in a noisy way, and you want to denoise. You want to remove the noise smooth it, without removing the details. The point here is that you're given intensity level at known pixels. The pixels are known, the locations are known, and the only thing you don't know is the intensity, and that is the noisy. You want to remove intensity noise. Yeah? And so here there's no question of where the data are, but here there is. Okay, if you now have a triangle mesh, so this is what you have is something like this. Okay, so you have a three-dimensional body, and the surface is described by a triangle mesh, and the unknowns are the like last lecture, the nodes of the triangles in this case, not of in 2 dimensions. In surface mesh, I guess it's 2.5 dimensions, you would say. And here it is rendered. Okay, the same triangle mesh is rendered for another body, obviously. This is for a famous Greek statue called Igea. And so now you're given again a noisy triangle mesh, and you want to denoise it. But now you see each point is x, y, z, yeah? 3 coordinates, and it involves everything. It involves the location as well as the intensity, all bundled up. So when it is noisy, you don't know the locations. So the dimensionality goes from 1 to 3, not from 1 to 2. Yeah? So that's one example. Again, I will talk about it next Thursday. I don't want to steal the show, and so let me just mention this and move on. Just to show you that it works also for another example. Okay. Let's go back to this. Okay, so a bit more quickly. Let's go back to this. Once again, the same Dupere equation. And now this S sub 0 is a known stock price, but actually we don't know it because it is really an average of in the best case, it's a given average of the prices of the stock over a day of trade. Okay, it could be worse than that, like the last one recorded, for example. If it is an average, then at least we are in good shape because we can define S sub 0 to be a new unknown with what we called S sub 0 is now S sub 0 hat, what is given on the particular internet site. And we can assume that there is a simple, distribution and so on. And so adding this sort of prior to our Tikhonov type regularization is a natural thing to do. And so now we have S sub 0 and MH, the discretization of this surface function Fm. Okay. The point is, however, is that remember we had K, but then we defined the y here to be log of K over S sub 0. If S sub 0 has uncertainty, then y, the location, the independent variable suddenly has uncertainty. Fortunately, it is a one-dimensional uncertainty. But still, it is an uncertainty that creeps into the locations of the data. Here, it's a relatively simple one compared to this triangle mesh. And so we know what to do. We basically add this term to the previous phi. Okay, and now again, like last Tuesday, we have a natural splitting of the unknowns. We have this M sub H and S sub 0, and they're only weakly coupled. They're not directly coupled at all. They don't depend really on one another. And so it makes sense to do the obvious, mainly you freeze S sub 0. Now you're back into the previous problem, and you use the same code you used before. And then you freeze MH, and you have only S sub 0 to solve for. In this case, it's a scalar. Yeah. We know how to solve scalar problems. And you iterate, and after 2 iterations is over. And it results in 1 or 2% change in adjusted price. And if you believe in the model, this could be a lot of money. So you see, these questions also arise, and you have to be aware of them. It's a good idea to be aware of such situations. The next one, forced to cut corners, is my favorite thing to think about when I have time to philosophize. I look at this. So it turns out, it's been claimed with lots of, how would I say, what's the word? Emphatically claimed that that when you when you try to find oil off the, close to Cabo Frio, for example, is it somewhere there? And so exploration for oil, you have to solve the full inversion, full waveform inversion problem, a famous problem. And Felix, my friend and former colleague, says you've got to have the velocity to have a chance of solving the full waveform equations and full waveform inversion, sorry. And we don't have them, and so he's been busy for, I don't know, a decade completing the data so that he will have what he needs in order to solve the full waveform inversion problem. Otherwise, he cannot do that, he said. There's a thesis by Kurt da Silva from only a few months ago in which their papers are described. They use tensor completion. It actually leads to some pretty fancy mathematics, in fact, doing this completion. We actually, if you recall, I don't know if you recall this example, that was this on Tuesday when I used the PowerPoint presentation, that problem. Okay, so first of all, before we move on to the graphics, this is the classical, again, I think that most people have seen this picture. You want to find whether there is oil underneath the seabed. And so you have a ship going, and it has this cable. And here there are guns making noise. And you have receptors that receive, that measure it. And so you measure reflections. And from this, you want essentially to recover the speed of sound, which is affected, of course, if there is a layer here or not. Very schematically. Okay. And the same thing, again, for those who have been here 2 days ago, we had something similar, in fact. I mean, we started with point clouds here. These were our measurements. We did motion tracking, and then the data were the results of the motion tracking, okay, and so on. And the obvious question is, why not start just, in fact, I was asked this by someone who is not here today, that guy from Florianopolis, a student from Florianopolis. Precisely this question. Why not just move from the data, which is the point clouds, directly to find the material properties? Why stop in the middle and say, oh, this is now my data for the next stage? Because now the data for the next stage is what we ourselves invented. Not invented, but produced. Definitely they are not IID, without a doubt. Okay, so I asked Bin that, even before, I forget his name, mentioned this 2 days ago, in fact, a few years ago, before we wrote the paper, and she said, I tried to do it, I cannot do it. I have to, first of all, do this, find the data from the tracking, and only then do the rest. I mean, it does not work otherwise. It did not work otherwise. And of course, this is kind of a negative result that you wonder, maybe if you do it right, then it will work. Yeah? But there is an issue here. An issue which is actually interesting to investigate, in my opinion. Again, the issue is eerily similar to this problem. Both of those are like the PD is hyperbolic more than, I mean, it's not heavily parabolic. There is some damping, but the damping is not so strong as it is in many other problems that we are used to. And so the problem is not so ill-posed. But on the other hand, solving the optimization, you have extremely non-convex objective functions, and actually it is worse. Of course, if you get results, they could be better because the resolution could be higher. Felix claims that, this, in fact, the fact that this is more hyperbolic type PDE also affects the kind of intuitive justification for doing more data completion. Adriano, that's a problem to work on, in my opinion. I think that that's actually an interesting research question that I don't think has been resolved. let me show you what has been resolved. This we've seen this before. Let's move on. So the point is that I've just said. Let me just say that if you want to look at the slides that Antonio is putting up after my talks, that the key observation here is written in a different color. They just have not, trying to cut it in the middle, without cutting it in the middle, without committing the crime, they could not solve the problem. So I'm supposed to, I have a lot of time. Yes. Yeah, okay. For some reason I thought that in 15 minutes I should be done, but no. On the other hand, good news, I will finish well before 5:30. Any questions so far?
When you find new type of regularization, there was a component that you said is coming from a prior information.
Yeah.
So in the end, if you have this scarce data, are you not fixing the values of M in those locations to be exactly the prior?
So it is not exactly. It is not exactly. Sorry. So the question was, before that, there were scarce data. Okay, so there were many solutions if you didn't have Tikhonov. Tikhonov type. I always say Tikhonov type here because, but then now that you have it, basically you introduce some prior. Does that fix it? Yeah. And so the answer is more complicated than this. I mean, you add more information. Okay, that gives you a solution. Then you have to somehow assess the solution. It's not trivial, and the books have been written on just how to assess the solution. Okay, in the case that I showed with the many equations. Come on. This one, there are those Tikhonov parameters here, alpha 1, alpha 2, and alpha 3. If you play with those, then you will get different results. Okay, so it's not as simple as I take A and B and now I have the solution. That's it. There's more to consider here. And in fact, people have asked how are we going to fix alpha 1, alpha 2, and alpha 3. But again, I suspect that people will discuss or have discussed this question in this sequence of courses. I don't want to suggest that in 2 minutes I will finish talking about everything. But there's a question of how to do that in this context when you don't have so much data. Can I continue? More question? Okay. Suppose that instead of having one set of data, you have many set of data. So here, what we wanted to do is to have, so f of m was p times g of u, where this is applying to q. Okay, q was a source, gu is the Green's function, depending on m. Sorry. And p was the projection to where the data was. Okay. What about if you have several sets of data? In fact, in the geophysical experiment, there were 3 frequencies there. I don't know if you noticed. 3 frequencies were mentioned. So there actually were 3 sets of data for each of the frequencies where that data was measured. So in general, we are going to say that there is a source qi, okay, depending on the frequency in the case of the geophysical example. The same Green's function and the same projection to the data, and where the data is measured, okay? And the result will be fi. And so now we want m such that fi of m is equal to di up to noise eta I for a whole set of experiments. Okay, that's our next setting. Many right-hand sides. And for example, in DC resistivity, that's, by the way, in the context of EIT, people talk about direct methods and not this one. But it is a more restricted setting. In geophysics, they all talk about, in exploration geophysics, I would like to correct myself. In exploration geophysics, they all talk about many sets of data. So here is this was called sometime the mother of all problems. Div mu grad u equal to right-hand side. And we are looking for mu of x. And here are the sources qi. And you will wonder, why do I call this mu and not m until now? And the answer is that often there is more. This is a difficult problem to invert, in fact, to find m, or to find mu. And sometimes we introduce more information by saying that m of x is a pointwise function of this mu. For example, maybe we know upper and lower bounds. And we can introduce the upper and lower bounds by using a hyperbolic tangent like this, something like that. The connection between mu and m would be through something like this. And now you introduce the fact that you have a restricted range in your values, and that is why m is a function of mu rather than what appears in directly the conductivity. DC is direct something. Direct current resistivity. That's what happens after 5 p.m. Yeah. So, thanks. And G of m again is the inverse of this PD. Discretized. And so for different QI, we get different fields, UI, and we compare that to different data sets, DI. And typical experiments would be, let's say that we have a square. So now we become mathematical, no longer funny domains, just a square in 2 dimensions. And we have points here and here. And we have sources which are delta function here minus a delta function here. And we vary the location. So we have p points here and p points here. Then we get p square experiments in this way. And they're measured here and here. Okay, we want to measure it not where we have delta functions in the source. I lost part of it, by the way, somewhere. Yeah. I hope it can be found. And so there are some actually values here of the minimum and maximum of mu and so on. We did it on a 64 by 64 mesh and additional data that are not important for us. So here's an example. The true model is green background of value 0.8. And this guy here has a value -2, and this guy here has a value of 0. Okay? And so one of them is above and one of them is below the background. And with about 4,000 experiments, we get this reconstruction, which is actually pretty good approximation to the real thing. Here, this is a pretty reasonably small, shall we say. Whereas if we do it only with 50, we get this mess. Okay, so it's useful to have many sources in this case. The problem is that each time you evaluate phi of m, remember the objective function? You have to solve 4,000 PDEs. Each time, for each iteration, for each purpose. Yeah. So you can actually get a lot of PDE solutions. I mean, one of the slides will show 500,000 PDE solutions in some situation. It's expensive, and in fact, prohibitively expensive. So the larger S, the better. But the cost of the solution grows linearly with S, if not worse. And we want to find something more efficient. So we look at what we can do is we say we have these Fs. So now there are Fi's. So we're going to form a matrix big F, which consists of F1, F2, F all the way to Fs. And similarly, the data, also there's a DI, D1, D2, DS. And so we are looking at the matrix function F minus matrix of data D. Each of these guys has L, just like before, L data points, but we have S of those guys. Yeah. And so now the least squares norm of phi is in fact the Frobenius norm of this F minus D, which we call B here. And the Frobenius norm, in fact, is equal to the trace of B transpose B. So if we call B transpose B A, then A will be semi-definite, symmetric positive semi-definite. It could be and will be often singular, but otherwise it's like almost positive definite. And for this trace, we can say that if we take random vectors from a certain distribution that has to satisfy some regularity condition, and we evaluate W transpose AW, and we do the expectation of this, that is equal to the trace, and therefore it is equal to the objective function. So here is statistics creeping through the back door, yeah, probability, I should say. So the distribution, by the way, should satisfy that the expected value of W transpose W is identity. So you have the entire space eventually. So approximating the expectation here is the same as approximating 5M, which is the trace of this matrix A. And so we do it by Monte Carlo approximation. We say the trace of A is equal to 1 over how many we have here random vector. We draw random S sub k random vectors in the kth iteration and evaluate, here's how we evaluate it. A times Wj, okay? So we take a vector Wj, evaluate A times Wj, which is another vector, and then inner product with Wj. So we don't have any matrix here. You have to realize that, this matrix, I mean, if we actually form this matrix, the A, then it's extremely expensive. Then you have solutions of A times Wj, and S is 4,000, let's say. Then you have 4,000 PD solutions. What we are trying to do is not do that. So if you only evaluate A times vector, you don't have A. Assume you don't have A. If you evaluate A times a vector, then this is only one, right? It's a one PDE solve. Okay? And so if this number S sub k is much smaller than S, then we are ahead. I think that some people sort of digesting it. It's late.
It's shocking.
Shocking, yeah. Well, it's actually quite simple if you once you get used to it, it's quite simple, in fact. We still have to ask whether we can get away with that. Oh, yes, and I should also say that Wj transpose AW, I don't have to form A at all, and I don't even have to form B, because A is B transpose B. So you're looking at the least squares norm of matrix vector product with B, where B is F minus D. just to show you that this makes sense, I'll come back to how to do it. So this is a comparison. So here the Tikhonov type regularization is total variation, which means like the approximation of the L1 norm of the gradient. L1 norm of the gradient. And if you're looking at 4,000 more or less right-hand sides, then if you apply our algorithm and solve everything that comes in sight, you need almost 500,000 PDE solves. And if you do it with 49, you get about 6,000 PDE solves. And if you draw these W's from a Gaussian distribution, a normal distribution, then you get about the same as the vanilla. So with 4,000 sources, you get about as many PDE solves as the full thing with 50. But the results are much better. So you actually are gaining quality without paying more by using this randomized algorithm. It's a randomized algorithm. Why total variation? Because that's a great question, and the answer is not clear at all. The total variation works better. So okay, I do have an answer. So on the shallowest level, first of all, this basically says I know that the true model, the true M is piecewise constant. Therefore, I know that it has jumps between the green and the brown and the purple. Yeah. And so total variation does not penalize jumps, whereas if I had least squares there, it would penalize it much more. It would smooth it. And I don't want it smooth. I want to actually retrieve it better. So you can see that here, in fact, you can see pretty clear jumps between the blue and this background and this, relatively speaking. If I use least squares, it would be much more smeared everywhere. Now, the reason why I needed so many words to say this is because, so here's another secret. Today is the day of secrets. Another secret, practical secret, is if you don't have enough right-hand sides, total variation could be worse. Even if though you're using more information compared to least squares, by saying, oh, I know how it should look like, total variation can actually be worse if you don't have enough information, if you don't have enough experiments. And I'm going to show you an example like that on Tuesday. Now the problem is that what happens if the P, so what we assumed is the following. So we're looking at what? So our B is P times Green's function times Qy. And we are looking at the sum of weights. These are the drawing of the vector W. Wi, P, G, Qy. And basically, the trick here is that this W is moved over here. And so this is sum of PG, Wi, Qi. So what we do is we form a new source, which is the weighted sum of the previous sources, and solve one PDE instead of many of them. Yeah? For each W, we solve only one PDE, sum of Wi, Qi. And then from each iteration to the next, for different W's, we vary the W's, yeah? the weights. But the point is that PG is the same, so G is solve for this right-hand side, for this source. Okay? So project and then project. But what if P depends on PI? You cannot do that. If P depends on PI, you cannot move Wi here anymore. And then the whole thing collapses. So our whole great way of reducing from 400,000 to 4,000 disappears. And what does it mean that P depends on I? It means that for different experiments, you measure the data in different places. And that is, in fact, unfortunately, that is the case with the boats and the geophysical experiments to find oil under the seabed. So in this case, what you want to do is complete the data, right? I mean, you have different PI. Each one of them corresponds to different places where you measure the data. How about the union of them? If I have the data everywhere where one of the experiments is measured, then I'm happy and I can produce this. Yeah? And so I have gamma I. For each I have a gamma I where the data is measured, and I want to look at the union of the gamma I. And so I want to interpolate or somehow approximate along the boundary, along where the data, in this case, is boundary. Yeah. I want to interpolate or approximate somehow. That's the data completion. And I have a great bonus if I succeed to do that correctly. Yeah. So what can you do? So if you want to be chic, you do wavelets or something like this. And people have done it, except that here it doesn't necessarily make sense because this is an elliptic problem. Everything is smooth, so wavelets are not necessarily the obvious basis here. Okay, but to confess our crimes, we actually started with wavelets because that was the in thing to do, as they say in English. Then came Kees van den Doel and said, come on, why are you doing this? Fred Rooster, so this is work with Fred Rooster and Kees van den Doel. Kees was a research associate, was a research associate. He's now working for a company, for a geophysical company. And Fred Rooster was my PhD student at the time. And so then we looked at piecewise linear interpolation and then also adding smoothness. This is, again, like a Tikhonov type element here in a simple situation. Minimize, find V that fits the data, but with this kind of prior, again, a prior. That depends on the gradient. And then likewise, if it is even smoother, one that depends on the Laplace-Beltrami operator here. Of course, here you also have Laplace-Beltrami when you take the variational equations. The question is which method to use. And once you get used to the idea that you shouldn't look at wavelets, the answer comes clear. By the way, Adriano, who is sitting here, helped us in setting things right here. And there's corresponding different spaces that had to be looked at in order to prove theorems about this. It turns out that here, in fact, there's no reason not to honor smoothness, okay? Which is, wavelets don't do that. And in fact, the options 3 and 4 here are the ones that remains relevant. Either this guy or this guy. Which one? It depends. If these bodies that have a different value than the background are all inside, then along the boundary, it is smooth. So use the smoothest option over here. If they touch the boundary, then there will be jumps there, then use this. And there's a connection between how you do the data completion and questions such as smoothness. So yeah, if there are discontinuities only away from the boundary, then use that Laplacian. Otherwise, what I called here L2G, which means gradient method, but in the L2 node. There are a bunch of theorems that justify this, and there's a paper that we wrote in 2014. So if it's smooth, that's a result of option 4. If it is piecewise continuous, then that's a result of the third option, L2G. And now we have a fighting chance. Okay, so here it is. This is noise 3%, the same example. And we need to do data completion only on 20%. Basically, remove some of the values we have. Yeah. And pretend, and now try to see what happens if we don't have them anymore. There is a method called random subset. Random subset is a method that basically says, I have S experiments, but I'm going to randomly choose only a few of them, okay? Kind of primitive compared to using a distribution, a normal, reasonable, normal probability distribution, or something that is called Hutchinson that I will talk about on Tuesday. Okay, so this guy does not involve any data completion. This one does. Okay, so and this is Gaussian distribution, and you can see that the Gaussian distribution gives a faster, converges faster by usually. This is actually a usual factor 2.5 better. But we have to make sure that the result is still good of the data completion. That is the point of this talk. Okay, so for 20% we get very good results. Data completion justified. Okay, for 20, here's another one, but here there are discontinuities in the first derivatives, yeah, along the boundary. Okay, so now we need the third option, L2G, I called it. And, but otherwise, the results are the same. The factor of 2.5 here faster than the random subset, and the results are still good. Okay, both of those work. If now, of course, we increase we want to see where it breaks, if it breaks. And 50% is more or less breaking point, let me tell you right away. So again, this is more economical, okay? But the results of the random subset are better. I mean, here suddenly there is an artifact that should not have been there, okay? And likewise here, you have these things that we don't have with the random subset method, okay? Yeah, if you, well, we actually showed that when it was 20%, the results were really comparable. Okay, so. Yes, we actually could check that. So we run it a few times, and this is sort of a typical average case. And when you compare the cases, you get basically similar results. It will not be the same, but there are. Yes. So this is a typical result that you get. It's not the only one we ran. Yeah. So you go to 75%, then the data completion breaks. So in fact, here we have this situation where there's really reason to use data completion, but you just don't want to do it when you have to complete too much. So of course, that was the conclusion that we concluded right away, the first case study. But here, there's a way of quantify that in more closely because we have this method that is similar to this guy, except that we don't use data completion. So the conclusion is right here. So I managed to, let me tell you what will happen on Tuesday, because it's a long time from now. So there was a meeting that George organized in Cabo Frio a few years ago, and that was when we only had the paper. We didn't have this paper, but the previous paper on the same topic, and Fred was a young PhD student. And we exposed these results of the first paper. And Pierre Degon, he's a great guy, he was in the audience. And after that, he said, he met both Fred and I, and he said, what about theory? I mean, I showed you actually a theory for the completion, but the theory for the thing itself, even if you don't have data completion problems. And my student Fred decided that what Pierre said was more important than what his supervisor said, because what I said was, come on, we need to solve it for more than one example. I mean, we need to look at other PDEs, and we need to. I wrote it somewhere here. Where was it? We need to actually check other situations and so on, and not to be glued to one PDE. But instead, he went and did a great job on the theory of this. And in fact, that will be the topic of Tuesday's talk. Some theory of randomized algorithms for this type of problems. I'm done for today. Any questions? Without a doubt, you're talking about forward nonlinear. Okay, I mean the inverse. The M appears usually nonlinearly. It is the U that appears linearly. Surprisingly, many problems in practice, in fact, are linear in this sense. It's not only the DC and the EIT, but many other problems that many other people here have worked on, in fact, appear linearly in the forward. If it is nonlinear, yeah, lots of other difficulties arise. It is nonlinear in the example I showed on Tuesday. And then you have a whole load of other difficulties in addition. Yeah.
So if I understood, you showed to us on Tuesday next week other type of key for this.
So what will follow on Tuesday is, so there was this matrix, and we are trying to estimate its trace. And the question is, how successful are we in estimating traces of implicit matrix in this way? So that will be the first part of the talk, is what's independent of this application. Just, is there a bound on it? I mean, does it depend on S? What if I have a budget to run 50 PDs? Do I have a chance to estimate the objective phi of M in a reasonable way, even if S is very large? Things like that. It turns out that there is actually an answer to this question, to my surprise. And also what properties of the matrix. Even if you don't know the matrix, maybe there are some properties that you know from the applications where they arise. And so there will be theorems like this. And then, so there will be sufficient bounds, and then there are also necessary bounds, how much you really have to have. And out of that comes an algorithm, in fact, as well, of choosing parameters. It touches even on machine learning. There's a lot of work nowadays on randomized algorithms, by the way. And that will appear again also in the lecture of Thursday, next Thursday. But one of my favorites is called the patch match. You know, how can you forget a name like that? Patch match, if you Google patch match. And he does data, so this is image processing, and you want to do a variety of manipulations on an image. And basically where you're lacking in data, in the image, you take part of, you know, it's like surgical operation of some sort that is popular in South America, in fact, among women, to remove, and so on. And so it randomly selects a patch in order to do completion of missing parts and so on and so forth, but in a clever way, yeah, not just randomly, but it finds something good, and then it looks around to find something even better, and so on and so forth. And it does a very good job compared to what our community, in fact, does when it comes to questions of image completion, and even more so image painting, in painting. In fact, this algorithm does a particularly good job on in-painting. I'm digressing here. But. Okay, I'm done.